Hello everyone, this is Mr. Molo for lesson 6-1, Properties of Exponents. So normally when we're in school, this is a 3-day lesson with normal, 45-minute classes. So now this year's going to be a little different, obviously. So we're going to see if we can do this in 1 day. And the most that this video service allows me to record is 15 minutes. I assume it'll probably go longer than 15 minutes, so we'll be on the lookout for part 2. So first we're going to go over the vocab here. So we need to know what a zero exponent is. So a zero exponent, that means anything to the 0 power. Anything to the 0 power is 1. Doesn't matter if it's 4 to the 0 power like it is in the example, or 10 to the 0 power, or 1,000,000 to the 0 power. Anything to the 0 power is 1. And that's also true for variables. So if you ever see like a to the 0 power, it doesn't really matter what a is. You might say, well, Mr. Mola, we don't know what it is. It doesn't matter what it is. It could be 4, it could be 10, it could be 1,000,000. Doesn't matter what it is. It's 1. So anything to the 0 power is 1. Okay? Negative exponents. So there's a cool trick for negative exponents. And so it kind of says something there that 4 to the negative second power is the same as 1 over 4 to the second power. I usually don't like writing it like that. I like writing it as numbers. So I'm going to compare it to a positive exponent. So if I have like 3 squared, 3 to the third, and 3 to the fourth power. So these are just normal exponents. You've seen these before. So 3 squared, we know is 9. 3 cubed, we know is 27. 3 times 3 times 3. And 3 to the third, or 3 to the fourth, we know is 81. So let's pretend those were negative exponents. 3 to the negative second, 3 to the negative third, 3 to the negative fourth. So the cool trick with these is it's the exact opposite of what it would be for the positive. So instead of 9, it's 1/9. Instead of 3 to the negative third, it's 1 over 27 instead of 27. Instead of 81, it's 1 over 81. So with negative exponents, it's really just the opposite of what the positive exponent would be. Notice how there's no negatives actually in the answer. It's not negative 1/9, it's not negative 127, it's not negative 181. It's just the positive version flipped over, and that works for all numbers. So same thing, if I did 4 squared, and 4 to the third, and 4 to the fourth, well, 4 squared is 16, and then 16 times 4 is 64, and then 64 times 4 is 256, and the same thing works for negative numbers. So 4 to the negative squared is 1 over 16. 4 to the negative third is 1 over 64. And 4 to the negative fourth is, 1 over 256. Okay, and the reason why, I'll show you on a new page, is if we think about it, go back to 3's again. 3 to the fourth power, 3 to the third power, 3 to the second power, 3 to the first power, 3 to the 0 power. Okay, so we already established this was 81. This was 27. This was 9. This was 3. We're kind of seeing a pattern here. From 81 to 27 to 9 to 3, we are dividing by 3 each time. And to continue that pattern, it only makes sense. Let's keep dividing by 3. 3 divided by 3 is 1. This works with any number, not just 3 and 4 like I'm doing for my example. This works for any number. And then if that trend continues with negatives, -1, -2, -3, -4. If you have a calculator and don't believe me, 1 divided by 3 is exactly what it sounds like, 1/3. That's why 3 to the negative first power is 1/3. You divide 1/3 by 3, you get 1/9. You divide 1/9 by 3, you get 1/27. You divide 1/27 by 3, you get 1 over 81. So 2 different ways to think about it. You can either continue the trend, or the fast way that I like to think about it is 3 to the fourth is 81, so 3 to the negative fourth is 1 over 81. 3 to the negative third is 1 over 27, because 3 to the positive third is 27. 3 squared is 9, so 3 to the negative squared is 1 over 9. 3 to the first is 3. 3 to the negative first is 1 over 3. Okay, so kind of some tips there for when you deal with negative exponents. Okay, and then we have product of powers. So the simple rule here is if they have the same base, which in this case they do, the base is 4, we just add the exponents. So 4 to the 6th power times 4 to the 3rd power. Really, we're just adding 6 and 3, and we get 4 to the 9th power. So another way to think about that is if I have 6 4s, and then I have 3 more 4s, pretty much just how many 4s do I have? A faster way to write that, instead of writing out all those 4s, is 4 to the 9th power. Okay? Dividing is pretty much the exact opposite of multiplying, like it should be. If I have 4 to the 6th power divided by 4 to the 3rd power, it's kind of like I'm subtracting those then. So 4 6s, I get it again, 6 4s in the numerator, because it's 4 to the 6th power, and 3 4s in the denominator. We can cancel some of those out. And I'm just left with 1, 2, 3 4s. So 4 to the 3rd power. So when you have a division problem, you're really just subtracting the exponent, again, as long as they have the same base. So we had 6 4s and 3 4s, then that works. If I had 6 7s up on top, then that doesn't work out. A 7 and a 4 don't cancel out. Okay? Then we have something called power of a power. So 4 to the 6th power to the 3rd power. So we have 2 of them. And so what that really means is I have 4 6 times. So 4, 4, 4, 4, 4. And now I have that 4. There's 4 to the 6th power. But then you have that 3 times. So there's 1 time. Here's 2 times. And here's 3 times. Well, we're not going to want to write this out every time we have all those numbers. So a faster way to do it is just to multiply those exponents. So instead of saying 4 to the 6th power 3 times and writing out 4, 4, 4, 4, 4, 6 4s 3 times, we can just say 6 times 3 is 18. And if you count all these up, that's really 18 4s. So it's the same as 4 to the 18th. So if you see one that has a power of a power like that, you're going to multiply those exponents. Okay? And then you'll get stuff like this, where now you have 2 numbers in there, and then there's an exponent on the outside. So when that happens, we need to distribute that 5, or whatever that exponent is, to both. So that's the same as saying 3 to the 5th power times 2 to the 5th power. So they're just distributing that exponent there. Okay, and then the same thing works if it's a division problem as well for this last one here. So 3 to the 5th power divided by 2 to the 5th power. So remember, when we distribute things, you just distribute it to everything. You don't get to pick which one you distribute it to. If there's parentheses around it, it gets distributed to everything. You're not just picking which one it gets distributed to. And then all these rules are also true for just variables. So that m would get distributed to the a and the b. That m would get distributed to the a and the b. It's all the same. Okay, now that we're done with the vocab, and we're about 8.5 minutes in, let's actually go look at some example problems here. And what's nice about this packet is it kind of splits it up for you, kind of the same order that I just did it in. So here's our rules for stuff like this, and it even tells you to write the rule then. So we have 2 squared times 2 to the 3rd power. So this looks a lot like the second one I believe we did, where we're just going to add those exponents. So if you have something that looks like this, our rule is we add the exponents. Okay, so 2 to the 2nd power and 2 to the 3rd power. 2 plus 3 is 5. It becomes 2 to the 5th power. Same thing here, 4 to the 1st power and 4 to the 5th power. 1 plus 5 is 6. We are adding the exponents. Same thing here, 5 to the 3rd power and 5 to the 8th power. 3 plus 5 is 8. We add the exponents. And like I said, it doesn't change with variables. I have 2 x's and 6 x's. I add those together, I get 8 x's. So no difference whether it's a number or whether it is a variable. Okay, and then the next set of problems we did was division problems. And remember, our rule for division problems is we subtract the exponents. Okay, so if I have 4 3s on top and if I have 3 4s on top and 2 4s on the bottom, 3 minus 2 is 1. So that's really like 4 to the first power. Same thing on example 2 there. 5 2s on top and 2 2s on the bottom. 5 minus 2 is 3. So it's really like 2 to the third power. Again, doesn't change for variables. X to the 6th and x to the third. 6 x's on top, 3 x's on the bottom. 6 minus 3 is 3. And then here, 3 to the 4th power, 3 to the 4th power. So 4 minus 4 is 0. So 3 to the 0 power, which we know is 1. Okay, here's our power of a power stuff. So now our general rule is we multiply the exponents. Okay, so we have exponent of 2 and exponent of 4. 2 times 4 is 8. So 2 to the 8th power. Number 2, we have an exponent of 3 and an exponent of 2. So that means it is 7 to the 6th power. Okay, same thing. Variables don't change anything. The y has an exponent of 3. There's a 3 on the outside. 3 times 3 is 9. So y to the 9th power. And again, on the 4th one, exponents don't change anything. X to the 4th times x to the 2nd. 4 times 2 is 8. And then the last one had those parentheses in there. Oh, sorry, we got 2 more. So 2 times 5 squared. So remember that this gets distributed to both. So 2 squared times 5 squared. So our rule here, distribute exponents to both. Actually, we'll say all in case there's ever one with 3. Okay, and then here we have 5 times 4 cubed. So that means 5 to the 3rd power times 4 to the 3rd power. Same thing here, 6a squared. That means the 6 gets 1 and the a gets 1. These are a little tricky because people like to think that they're different, or like they're the same, but they're not. So 6 squared and then a squared. And then same thing here, the 3 gets squared and the x gets squared. So even though you don't see a multiplication sign in the middle, just like up here on example 1, that says 2 times 5. Example 3 doesn't have a big dot in the middle telling you it's a times problem, but we know that means 6 times a. Okay, now the last example problem. Okay, same thing. We are going to distribute exponent to all. So I got 2 to the 3rd squared. So that means that 2 goes to the 2 on top. That 2 goes to the 3 on bottom. So 2 squared over 3 squared. 4 thirds cubed. That means 4 goes to the 3rd power. 3 goes to the 3rd power. X over 2 cubed. That means x goes to the 3rd power. And 2 goes to the 3rd power. And then we got AB raised to the 4th power. That means A goes to the 4th power and B goes to the 4th power. So we're about 14 minutes in here. Like I expected, this is going to be a 2 video lesson. So I'm going to stop the video here. And then the next video we'll pick up on page 172 and do some more example problems.